Here are two more examples of integrals involving powers and products of trig functions. First, let's find the integral of the tangent of x times secant to the fourth of x dx. This problem is going to be similar to the problems involving sines and cosines in that we can use a u substitution here. But how do we choose our u? First, let's remember what the derivatives of tangent and secant are. The derivative d dx of tangent x is equal to secant squared x. And the derivative d dx of secant x is equal to secant x times tangent x. If you're having trouble remembering these things, now would be a good time to go back and review your derivatives of all 6 trig functions so that they're fresh in your memory, because it will be very helpful for you to be able to recognize the derivatives of these trig functions when you see them. What should we do in this case? As with our integrals involving sines and cosines, we're going to want to choose a trig function for our u substitution. And the trick here is going to be to make a choice for the du based on whatever appears in our integrand. And from that, the choice of u will follow. In this case, I'm looking at my integrand here, and I'm seeing that I have 1 power of tangent x, and then 4 copies of secant x to the fourth. So maybe I will split off that tangent x times secant x and group that with the dx. Of course, this is just multiplication. We can rearrange the terms here any way we want to. And what's left over is secant cubed x. And if I look at this, what I see is I see a function of secant x, and then I also see the derivative of secant x right here. So maybe let's let our u be secant x, and let our du be secant x times tangent x times dx, of course. So we're all set. Here's our u cubed, and here is our du. Very little effort here. So this is the integral of u cubed du. And that's easy to integrate. That's going to give us u to the fourth over 4 plus a constant. Fill in our u again. This equals secant to the fourth of x over 4 plus a constant. And that's our answer right there. Now let's look at a very similar problem with one change. Let's find the integral of tangent squared x times secant to the fourth x dx. The only change here is that I've squared the tangent this time. In the last problem, because the power on the tangent was just 1, it was easy for us to separate out tangent x times secant x to be our part of our du. And whatever remained was just a bunch of powers of secant x, which was our u, and that was easy. This time we can't separate out just tangent x times secant x because we'll have an extra tangent lying around that we don't know what to do with. Instead, let's try separating out secant squared x. This is equal to the integral of tangent squared x times secant squared x times secant squared x again, dx. What's useful about this is that one of our derivatives of our trig functions is right here. Secant squared x is the derivative of tangent x, and we have a tangent x right here. That other secant squared x we'll deal with in just a moment. So let's let our u be tangent x, and therefore our du is secant squared x dx. So we're all set. This is u squared, This part here is du. But we do need to figure out what to do with that secant squared x there. We can't just call that du. It is not du. Du requires a dx. We've already used up the dx. We'll need to find a way to replace that secant squared x with something involving tangent, because our u is tangent x. How do we do this? Let's go back and look at our trigonometric identities. In the last video, we made use of the identity sine squared theta plus cosine squared theta equals 1. Bear in mind, theta here can be a stand-in for any angle that you happen to be using, anything at all that is being plugged into your trig functions. If we take the first identity and we just divide both sides by cosine squared theta, we'll get tangent squared theta plus 1 equals secant squared theta, right here, the second one. If we take the first identity and divide both sides by sine squared theta, we get the third identity. In this case, the second identity here is the one we want, because it will allow us to replace secant squared theta, which we don't want, with tangent squared theta plus 1, which we do want. Let's go back to our problem and make use of this. I'm going to rewrite that identity, but I'm going to put the x in this time instead of theta. So we know that secant squared of x equals tangent squared of x plus 1. Now we can modify our integral. This is the integral of tangent squared of x times, well, secant squared x is being replaced with the expression tangent squared of x plus 1, in parentheses, that whole thing is being multiplied by the rest of the integrand, times secant squared x dx. And by the way, I recommend that you do not start replacing functions of x with u and du until you're ready to do that with the entire integrand, because otherwise you'll have intermediate stages that have u's and x's showing up in the same integral, and you may get confused about which variable you actually want to use. So I would say let's wait until your integral is in exactly the form that you want and you're ready to do the substitution in full. And now we're ready, because we have our du, secant squared x dx, and the entire remainder of the integrand is all in terms of tangent x, which is our u. Now we can do our substitution. This equals the integral of u squared times u squared plus 1 times du. This is an easy integral to do. We'll just multiply in that u squared as usual. This is equal to the integral of u to the fourth plus u squared. Put that in parentheses, that's times du. And now we can find the antiderivative. This is 1/5 u to the fifth plus 1/3 u to the third plus a constant. And as always, let's just fill in what our u is. This is equal to 1/5 tangent to the fifth of x plus 1/3 tangent to the third of x plus a constant. And this is our final answer. So what do we take from this? Well, any time that you have a product of powers of tangent and secant, any time that the secant has an even power, you can split off a secant squared x to be your dx, and whatever other secant x's are left over will still have an even power, and you can use this trigonometric identity to replace those secant squared x's with something involving tangent, which is your u. So if your secant x has an even power, then make your u equal to tangent x, make your du secant squared x dx, which is a consequence of that choice of u, and you'll be able to use your Pythagorean identity to rewrite the rest of the integrand to be in terms of tangent and do the u substitution. On the other hand, if your tangent has an odd power, then you can split off tangent x times secant x to be the du, which means the u has to be secant x. And as long as the tangent has an odd power, then you might end up with some remaining tangent x's, after you split off one of them, but they'll then have an even power, and you can use this same Pythagorean identity to rewrite those in terms of secant x. In fact, in the last problem that we did, the tangent had an odd power and the secant had an even power, so you actually could have made your u either tangent x or secant x. Either way would have worked. You would have ended up with a different looking result, but the two results would have been equal.